lesson is lesson 3, which is properties of rational exponents. And the cool thing is we've already talked about the properties of exponents, and the properties of rational exponents are all the same. It's just now we have rational exponents, which just means fractions, but the properties work the same way. So at the top, section 3.1, this one has two properties in it. So the one on the left, the product of powers rule, the one on the right, the quotient of powers rule. We're going to start on the left. So for the product of powers rule, the word product just means multiply. So anytime you see that rule, it has to do with stuff that are multiplying, or more than likely you'll have the problem and you'll kind of want to know what rule it goes along with. So example 1 is 5 to the 1/5 times 5 to the 3/5. So we have the same base, 5 and 5, and we're multiplying them. So we'll use the product of powers rule. Same base, multiplying is product of powers. And that property tells us when we add when we multiply powers that have the same base, we need to add their exponents. So we're going to add the 1/5 and the 3/5. And then remember, when you have a fraction or you're trying to add fractions, they need to have a common denominator. Ours already do. They both have a denominator of 5, so we don't need to do any work there. We can just go ahead and add them together to kind of simplify it into a single power. So I'm going to write that middle step though. So we'll do 5, and then it'll be 1/5 plus 3/5. And then when we add fractions, we just add the numerators. The denominators, the bottom part, doesn't change. So this would become 5, and then raised to the 1 plus 3, so 4/5. And then just kind of notice like the 5 stays the same all the way through, doesn't like change to 25. Our like kind of property tells us that we can condense it down into one power by just adding the exponents, and that is the only change that happens. So I have 5 to the 4/5 is my final answer. We don't want to put it in radical form or anything like that. That's not considered more simplified. The only way you would simplify it beyond this is like if we could reduce that fraction, which we can't. So we just leave it as is. And then the little note at the bottom we'll talk about after. So example 2, quotient of powers rule. And then the word quotient means divide. So similar kind of idea here. I'm going to actually zoom out really quick. So for the first one, we had multiplication and we added the exponents. For the quotient, we're dividing, right? Because like a big fraction is the same thing as dividing. So when we divide, we subtract the exponents. So like multiply, we add the exponents, and then divide is the opposite. So we subtract the exponents as long as their bases are the same, which these are because they're both 7s. So we can go ahead and subtract. We have 2/3 minus 1/4. You would always, actually, I'm going to finish the problem and then kind of go back to my thought on that. So we need to get a common denominator here right now. We don't have it. Right now we have a 3 and then a 4 as our denominators. So the common denominator is going to be what's called the least common multiple of 3 and 4. And just like a little review, a multiple is like a number that something multiplies to. So like 3, 6, 9, 12, those are all multiples of 3, and then for 4 it'd be 4, 8, 12. Those are all multiples of 4, so the least common one is the first one they have in common, which is 12. So in order to get a denominator of 12, I'm going to have to take my 2/3 and I'll have to multiply it by like a version of 1, but I'll multiply by 4 over 4, because that's like the same thing as multiplying by 1, right? 4 divided by 4 is 1. But now it's going to give me the common denominator that I need. So it'll end up being 7. And then with fractions, we just multiply straight across numerator and denominator. So it'd be 2 times 4, which is 8. And then 3 times 4, which is 12. So we're done with the numerator. And then for down here, the 1/4, to get that 4 to turn into a 12, I'm going to have to multiply by 3 over 3. So same thing, we'll keep our 7 the same, and then we will multiply straight across. So 1 times 3 is 3, and then 4 times 3 is 12. And then now we have a common denominator, so they both have 12 in their denominator. One thing before we move forward is you don't like necessarily always just multiply like by the other numbers, like this one was a 4 and this one was a 3. It just kind of depends like what can you multiply in to get to the least common multiple. It varies by problem. And then now I can go ahead and subtract the exponents. So it'll be 8/12 minus 3/12. So it'll be 7 raised to the 8/12 minus 3/12. And then same idea, we just have to subtract the numerator and then the denominator stays the same. So it'll be 7 raised to the 5/12. And let's say, like, for example, we had a larger, like, number or higher value exponent in the denominator. We could technically do, like, the exponent from the denominator minus the exponent from the numerator. Our base would just stay in the denominator and we would have a 1 in the numerator. So it'd kind of be like the reciprocal of what we ended up with here. So at some point we should have an example like that pop up. Okay, before we move on to 3.2, just like a couple of kind of important notes. So the first line says powers must have the same base, to use just these properties, not like all specific properties, but these two in particular. So basically when you're multiplying or dividing, if we want to add or subtract the exponents, they need the same base. And then the second line, fractions must have the same denominator to add or subtract. So if they don't have the same denominator, you need to get the same denominator. That does not apply for multiplication or division though. 3.2, there's 3 different properties here. So the first one is a power of powers, and that's basically when you have like an exponent raised to another exponent. So when that's the case, you multiply the exponents, which is kind of nice for rational exponents, even if they're like different denominators, because when you're multiplying, you don't need the same denominator. So I'm just going to kind of rewrite this horizontally. So 11 and then raised to the 2/3. And then when I have a power to a power, I multiply those exponents. So it would be 2/3 times 3/5. And then there's a couple options here. We can either multiply straight across and then reduce, or we can cross cancel, or you may have heard it, I don't know what other words to describe it, but I've heard a bunch of different things. So basically, like, I can reduce diagonally as well as vertically. So like the 3 and the 3, if I divide those both by 3, they become 1. And then now I can multiply straight across, and my problem will basically already be reduced once I finish. So it'll be 11, and then 2 times 1, right? Because the 3 went away. So 2 times 1 is just 2. And then in the denominator, I have 1 because the 3 went away times 5. So just 5. So I have 2/5. And then 2/5 can't be reduced any more than it already is. So that's our final answer, 11 to the 2/5. Okay, and then the next one, example 2, power products rule. So 2 to the 1/3 times 5, and then that all in parentheses is raised to 3/7. So power of products. So just kind of like dissecting the like title is we have products inside the parentheses. So two things being multiplied, and then those two things being multiplied are both being raised to that power. So power of products. So when this is the case, it's kind of like distributing. That's not technically the word that we use to like describe it, because distributing is just multiplying, and here we're kind of using an exponent on stuff, but it works in a similar way. So what that means is this exponent, the like 3/7, it gets applied to the 2/3 to, or sorry, the 2 to the 1/3, and then also to the 5. So the 2 to the 1/3, that whole thing gets raised to the 3/7, and then also the 5 gets raised to the 3/7. And then now I have another power to a power, like an exponent raised to another exponent. So that's kind of like example 1, where I have to multiply those exponents. So it'll be 2, and then I'm going to write it kind of horizontally, raised to the 1/3, and then times 3/7, and then times 5 raised to the 3/7, And then now I want to simplify these. So when I multiply them, remember you can either multiply straight across and then reduce, or you can cross cancel. And I see that I have these 3's again that I can cross cancel. So this is going to be a 1 and this is going to be a 1. And you're just basically like kind of dividing out a common factor. So if I divide both 3 and 3 by 3, they become 1. So now I can multiply straight across. So this is a 1 times 1. So it'll be 2 raised to the 1 in the numerator. And then in the denominator, it's 1 times 7. So 7, and then times, I'm going to bring down that 5 to the 3/7. And then here's where like you kind of feel like you should be able to simplify it more because I have these 7's both right here. But we can't because the bases are not the same. Like one is a 2 and one is a 5. So that actually just means that we're done there. So 2 to the 1/7 times 5 to the 3/7. Remember, in order to be able to like simplify the like ones that are being multiplied together like that, they need to have the same base. Like the bigger number needs to be the same. And then for the power of quotients rule, this one kind of works like the previous one where that exponent gets applied to both. In this case, we have a quotient, so the x divided by y. So the 7/8 gets applied to the numerator and the denominator. So it'll be x raised to the 7/8 and then over y raised to the 7/8. And then now we have a quotient where they both have exponents, but the exponents are the same, but the bases are not the same. So if the bases are not the same, then we're done and we can't simplify beyond that. So x to the 7/8 over y to the 7/8. And then 3.3 is all about combining like all the different properties together. So I would say that this problem is like more challenging for sure. If or excuse me, I would recommend watching it maybe one time first and then going back and writing it with me the second time basically. It's kind of like a lot going on. So it might be nice just to watch it one time through and then go back before you start copying it down. Okay, so starting them inside, 8y to the 3/2 x over 125y to the third power, or y cubed, and then that whole thing is being raised to the 2/3 power. So you've like worked with order of operations before. With exponents, there's not really an order of operations because exponents in itself is its own spot. So it's like what parentheses exponents, but it doesn't like decipher between which exponent property goes first. You just use whichever one you feel like. And then as long as you've simplified as much as you can at the end, that you're done. So the way that I do it could be different from the way that you want to do it or the way it is in the workbook, and we could all get to the same answer. So what I'm going to do first is I want to get rid of these parentheses. So this 2/3 is going to get applied to every single different factor inside the parentheses, and factors are things that are kind of being like multiplied by each other. So if it's helpful, you can kind of go ahead and like separate out the factors. So this is 8 times y to the 2/3 times x, and then 125 times y to the third power. So this is a factor. This whole thing is a factor. Here's another one. 125 is its own, and then y to the third power is its own. So that 2/3 gets applied to like all of those different things. So 1, 2, 3, 4, 5 different things. Okay, let me get rid of some of that. Okay, so now the 2/3, I'm going to take it, I'm going to apply it to the 8. So I'm actually going to go ahead and set up like my fraction too, just so I can kind of fill in. So it'll be 8, and then to the 2/3. And then I'm going to take that 2/3 and it's going to get multiplied by the, not multiplied, sorry, it's going to get applied to the y to the 3/2. I was getting a little ahead of myself. I'm going to put the little dot here just to separate and keep my work a little bit more clean. So I have y to the 3/2, and then that whole thing is going to get a raised to the 2/3. So from here, that gets applied to it as like an exponent on top of it. And then the next one, I have to take that 2/3 and apply it to the x, which that one doesn't already have an exponent, so it just becomes its exponent. So x to the 2/3. Okay, so we're done with the numerator. We still have to do the denominator though, so that 2/3 got applied, or is going to get applied to the 125, so it'll be 125 to the 2/3 power. And then now it has to get applied to the y to the 3rd power. So I'm going to put my dot there, just kind of separate it. And then I have y to the 3rd power raised to the 2/3 power. So it's kind of a lot, I know. I'm going to kind of go through and really briefly just show what each different part came from. So first I took the 2/3 and I applied it to the 8. That's how I got 8 to the 2/3. And then I took the 2/3 and I applied it to the y to the 3/2. That's how I got y to the 3/2 to the 2/3. And then I took the 2/3, applied it to the x, so I got x to the 2/3. I took the 2/3, applied it to the 125, I got 125 to the 2/3. And then I took the 2/3 and applied it to the y to the 3rd power to get y to the 3rd power to the 2/3. It's like a mouthful. But one more time, just kind of like as you're looking through, like basically I just added a 2/3 power to everything that was originally in my problem. Okay, and then now we can go ahead and kind of start simplifying like our power of powers. So I'm going to draw my line again, just so I can kind of fill in from left to right. I'm going to leave the 8 to the 2/3. And then right here, I have a power to a power, which means that I multiply those exponents. So these are going to be multiplied. I don't really want to write like a whole new step just for like, or a whole new line just for that step. So I'm just going to make myself like a little note of them being multiplied up here. So 3/2 times 2/3. So the 3's cross cancel, the 2's cross cancel. So everything's like gone. I'm just left with 1. So that actually means that these exponents are both gone, and I'm just going to have y to the 1st power. So that's kind of nice. Anytime you multiply a fraction by its reciprocal, it's just 1. And then for the x to the 2/3, there's nothing to simplify there. I'm just going to copy that over. And then I'm going to copy over the 125 to the 2/3. And then now I have another power to a power, so I'm going to multiply these exponents. I'm going to do the same thing where I just kind of write it off to the side. So it'll be 3 times 2/3. I'm going to think of that 3 as like a fraction, so I can see a little bit, I don't know, it makes it easier in my head. So I'm going to make it 3/1. And then you can cross cancel the 3's. Those both become 1's. And then if I multiply straight across, I just end up with a 2/1 or just 2. So in the denominator, I have a y squared. Okay, so moving on to the next step, this is going to kind of go back to an earlier lesson where we were changing things from rational exponent, like a fraction exponent, to a radical. And bear with me, I know this feels like a lot, and it is. So the little kind of trick that we would use to change from like a fraction exponent to a radical was if we had b raised to the e over r, we could turn that to radical form and be the r root of b to the e power. So that's actually what I'm going to do with my regular numbers, because a lot of times when I have regular numbers to fraction exponents, it's kind of tricky to simplify them, but both of these can actually be simplified. So in the numerator, this is my b is the 8, and then to e over r, and then in the denominator, b is 125, and then e is 2, and r is 3. So now I'll rewrite those in radical form. So for the 8 to the 2/3, the 8 is going to go inside the radical. That's my b. And then r, like the denominator, the 3, that's the index or the type of root it is. And then now I'm going to square it. And then I'm just going to copy down the rest of my like variable part of the numerator. So it'll be times y times x to the 2/3. And you don't need to put the dots, but you definitely can if you feel like it kind of helps keep your work a little bit more organized. And then now we're going to do the 125 to the 2/3. So the 125 goes inside the radical. And then my like r is 3, so that'll be my root. It's a cubed root. And then my exponent is 2, so that'll go up here. And then I just need to copy down my y squared next, just kind of making sure that it doesn't go underneath the radical because it is not part of like what was being raised to that 2/3 power. Okay, so now we're ready to simplify the radicals. I swear we're getting closer to the end, even though it doesn't really look like we're doing much simplifying. Okay, so the cubed root of 8, that's asking what number times itself, or like what number to the 3rd power equals 8. Well, 2 to the 3rd power equals 8, so the cubed root of 8 is going to be 2. So that whole cubed root of 8 simplifies to 2, then that's going to be squared, and then times y, just copying the rest of the line, times x to the 2/3 power. And then now on to the cubed root of 125. So the cubed root of 125 is asking what number cubed equals 125. So if I take 5 and cube it, that equals 125. Or if I take the cubed root of 125, that is 5. Okay, so the cubed root of 125 simplifies to 5, and then I still have that little squared over it from right here, so I got to include that. Same thing with like the cubed root of 8. And I'm just going to copy down the rest of the line, which is y squared, so times y squared. Dang, I really thought I left myself enough room, but this has kind of been a long problem. Okay, so I'm going to bring it down here, create my little fraction, and then go left to right in the numerator. So I have 2 squared, 4. I'm just going to copy down my variable, so times y times x to the 2/3 power. We're getting so close. And then in the denominator, I have my 5 squared, which is 25, and then times y squared. Okay, so really only one more step. So when you have, when you have the same variable in the numerator and denominator, it's more times than not, and probably every example that we'll see in Algebra 1, not simplified. So because, like, let's kind of say, you don't need to write this, it'll just be kind of a side note. If I had 8 over 64, so 8 over 64, like I know I can reduce that because I can divide it by like 8 in numerator and denominator. But 8 over 64 is like the same thing as 8 over 8 squared. And that's why I was able to reduce it, because it's like the factor in the numerator, it's just that same number being squared in the denominator. So you kind of have to think of variables that same way. So like I have a y in the numerator, I have a y squared in the denominator. There's something I can do to simplify it there. So basically, anytime you have a like one in the numerator and something in the denominator, or in general, you have to think of like each power canceling each other out. So this is a y to the first power because we don't have a exponent over it. So that y to the first power cancels out one of the 2 in the denominator. So one more time. This one cancels out completely, and then I'm left with, I had 2, I'm only left with 1 more. Think 1 and 1. So final answer, 4, the y in the numerator is gone, so x to the 2/3 power, and then over 25, and then just y to the first power now because one of the 2 y's that were there got canceled out. So 4x to the 2/3 over 25y.